actually incorrect in German. It should be okay. And in the last echo, it should be full.
All right, everyone, second talk by Manoj. Manoj is an assistant professor in the Department of Mechanical and Aerospace Engineering. His recent research has focused on the understanding of human locomotion and biomechanics from the perspective of optimality and dynamical systems theory. And he's broadly interested in a variety of biological and mechanical systems. Manoj got his undergraduate degree in engineering from the Indian Institute of Technology in Madras, his doctoral degree in theoretical and applied mechanics from Cornell, and he was a postdoctoral researcher and lecturer at Princeton. Manoj says that you can interrupt with questions during the presentation if you so desire.
Okay, I'm going to take a little bit of artistic license with conflict here. But we'll have, I guess we'll see where it goes. So this talk is broadly related to my research. Most people walk like that and run like so. And you might ask, why do people walk and run like that? And you might wonder if that's all we can do. And we know that that's clearly not true. It's a famous experiment. That's why. Who knows this video? I like to joke that this is a experiment done by a Cornell University professor, and it is actually true that he's a Cornell University professor. He was recently appointed, maybe 10 years ago, an honorary professor at Cornell. So that's John Cleese appointed by Cornell. He's a professor at Cornell.
For this?
What?
Was he appointed because of this or for the arts?
I think he used to be the something Andrew Dixon White Professor at Large. So he's a member of
Professor at
I don't know. I might be misquoting things, but I think
distributed
something
major.
like that. I think. Yeah. I think his responsibilities included coming and giving lectures once and twice a year, roughly. I'm not sure what he is right now. Okay, so we can do all that. So that's a lot of choice. So why do people walk and run like this? And how do we sort of bring the conflict, so to speak? And the answer is not all that surprising. I'm sure all of you would probably give the same answer. What's the answer? Why do we walk and run like that?
It's natural. Energetically favorable.
What?
Energetically favorable.
Energetically bearable, or better. Right, so you might say we don't walk like that because it's silly. So that's a reasonable answer. So that looks silly. In fact, this is called the Ministry of Silly Walks. And the answer many of us think is that we move the way we move because we minimize energy, or the way we walk and run minimizes energy. So people have done experiments over the last 15 years or so, where you change something and then measure energy cost as a function of that. So put a person on a treadmill, make them walk at various speeds, measure energy cost. Now, how do you measure energy cost? You measure the amount of oxygen and carbon dioxide they breathe in and out. And for every speed, you get a point. You measure energy cost per unit distance traveled. You get a curve like this. And then make a person walk naturally as they would. And the speed at which they walk approximately lines up with the bottom of this curve. People have done various versions of this experiment where you change something else, like stride length or stride frequency and all kinds of different things, and you plot energy cost as a function of that. In other words, you make a person walk on a treadmill with longer or shorter treadmills, like that, or really long treadmills, measure energy cost, plot this curve, and then ask the person to walk naturally, and the natural gait approximately is the bottom of that valley. So people think, again, at least approximately, that the way we walk minimizes energy consumption. And we can sort of build mathematical models, computational models that sort of bear out the same idea. You can make a model driven by muscles and which is capable of all kinds of crazy walking and running motions. And then you do an energy optimization calculation, you get things that look like walking and running. So this is walking at slow speeds. This is walking at a slightly faster speed or something, just slow motion. So you might say, at least from this sort of very basic evidence, one goal or one sort of, when we walk, of course, our goal is to go from A to B, but the thing we optimize is energy, at least. Again, I like to say approximately. But energy is not all we care about when we move, given that we can go from A to B. There are all kinds of conflicting goals, right? What may they be? For instance, you want to walk in a manner that you don't fall down. So stability is very important. In fact, stability is even more important probably than energy consumption. In that it's a necessary condition. You don't want to injure yourself. You don't want to put too much stress on your limbs. So these are all important goals. So how do you resolve these when you have these conflicting goals? So let me give you an example where there is a conflict between two of these goals. So I like to say, pull your arm out and close your eyes. Maybe put it on a table or something, and then sort of just observe your arm for a little bit. And then now imagine that someone next to you is going to hit your arm really hard at some unknown time. And your goal is to keep your arm as still as possible. Okay? Someone's going to hit your arm very hard in the next 15 minutes, 15 seconds, let's say, and your goal is to hold it as still as possible. So what do you do? What would you do? You think?
Tense.
Tense, right. What does tensing do? Right, so tensing increases your stability, right? So that's your goal. So you want to prevent someone from knocking your arm off. It increases stability roughly, but it uses more energy, right? So these goals are, at least in this particular example, conflicting, and there's no way around it. When you, well, if you do the same experiment with a person standing and you say, someone's going to knock you over in the next 2 minutes, how should you stand? Well, if you just want to minimize the energy, if you want to stand like I'm standing now,
I would lay down.
you would lay down, right? But the constraint is you have to stand up. Okay, that's a reasonable thing to do. Laying down is always reasonable. But given the constraint that only the feet can touch the ground, you would spread your legs like so. It wastes energy, right? So anything other than straight up wastes energy, but that gives you more stability. Again, just an example of how we trade off these in this case, conflicting goals. Now animals also do that. On sort of an evolutionary time scale, we think. And we pause this video. So cockroaches are tiny insects. And you will notice that cockroaches have relatively sprawled posture. So they're standing like this, right? So this is my sort of this is the bottom side of the cockroach. Imagine I'm a cockroach.
Ventral.
Ventral, that's right. Sorry, dorsal. I'm getting my biology back. Right, so imagine I'm a cockroach. So the legs are sprawled all over. And when they do run, they use what's called an alternate tripod gait. which means they have 6 legs. Let's see if I can do this so these are 6 legs. These 2 legs and this leg contact the ground, and these 2 legs and this leg contact the ground, and they do this alternatively. Right? And that gives them stability. Tripod stability makes sense. What?
And creepiness.
And creepiness as well. This is true. This is actually the friendliest looking cockroach picture that I found. I was careful not to pick up. So I typed cockroach into Google Images. There were very creepy images. This was
I've got some cute ones.
cute. I noticed there's one outside, right outside. If,
Madagascar is.
Madagascar, that's right. Although it's hard to see their sprawl legs on the. Okay, so this is the coolest experiment ever. Okay, first see what happens, and then we'll. Oops, sorry. So it's a cockroach. Let me pause it. It's a cockroach with a little jetpack. Back. And in a second, you will see a little cannonball shoot out to the right, and you will see what the cockroach does.
Nothing.
That's cool and a nightmare.
Okay, so what happened to the cockroach? So it's running pretty fast, and it barely breaks its stride, right? At least it's focused. Right, it's focused, and so it turns out, I mean, in terms of the amount of perturbation, so if you're walking at some speed, the sideways speed added by the perturbation is 80% of the forward speed or something. But that sideways perturbation gets killed within a step, right? So if you gave a sideways perturbation of that magnitude to a person, you would fall over very easily. Much smaller perturbations knock us off the ground. But nothing happens to the cockroach. So it feels like cockroaches, by adopting this sprawl posture, have traded off some energy consumption. They use much more energy, but they have much greater stability, presumably because they are adapted to their world. Their world is very uneven compared to the world we see, right? So that's at least the story that we like to tell. Yeah.
I don't know if this is relevant. This
Yeah.
either way. I can ask you after.
Yeah.
So clearly they went to a lot of trouble to put the jetpack on the cockroach. I assume that it was important that the force is coming from the roach instead of just blasting it with a blast of carbon dioxide or something, which would be, I would think, what most people would think of doing.
Yeah, that's a good
Making
question.
it wear clothes.
Yeah, so I think they maybe wanted
A jetpack?
I think that's the correct answer. That's the real answer. But what they would say is maybe that they wanted a really sharp perturbation, very small duration, large perturbation in a small duration. Well, I think this, yeah. Wind takes some time, I guess. Yeah.
Yeah, because I would have just decided to like blow something out.
Right. So that's a good question. So when specifically when all insects, you probably know this better than I do. All insects have these cerci which get activated. So they have little horns at their back, and if you blow on them, they have this incredibly fast reflex. There's a big neuron that goes from their back all the way to the front that triggers their legs, they run away. It's called the escape reflex. So if you use wind specifically, that sort of pathway might get triggered and you might get weird stuff.
And a jetpack wouldn't stimulate that.
A jetpack, the hope is that it doesn't, I don't know.
I think it would. I think that would make a difference, right? Because it's like there's nothing on them, and then suddenly they're blasted sideways. You know, like I think it would.
Yeah.
That is really cool.
Anyway.
I want to jetpack.
So here's more animals. There's a progression here. That maybe there is a trade-off between these goals of stability and energetics. And if you do plot sort of energetics as a function of animal size, big animals per unit mass are much more energy efficient than small animals. Okay, I'm very slow. There's a lot of videos, maybe I'll just skip over. So these are, sorry.
The bottom one?
There's a new one.
No, I guess.
Oh, my
So
kids
big
love
dots.
that.
So the ones on the left are all sort of more versatile robots that can walk on uneven terrain. The ones on the right are all very energy efficient robots. And these robots consume about 30 to 40 times more energy than a human. These robots consume about as much energy as a human does. These robots are barely stable. These robots are very stable.
It's two people with something.
Okay, so you can think about these sort of trying to figure out how to rationally reconcile conflicting goals using, well, if you just have a single goal, you can use optimization to find the optimal solution. But if you have multiple goals, you can resolve them using what's called multi-objective optimization to discover if you care about stability more, what should you do? If you care about energy more, what should you do? If you care about both equally, what should you do? Kind of thing. Should I go on for another 5 minutes? I guess there are some questions in between. Yeah.
Yes.
Right. So that's why it's a sneaky way to get more time. Okay, so muscles make us move. Muscles act on sensory information. We have all kinds of sensors. Our body is full of sensors. Every little inch has hundreds of sensors. And sometimes, these are all reporting to the brain or the spinal cord and so on. Sometimes these sensors can provide some conflicting information, and the brain has to figure out some way of resolving this conflict. Right? This is a famous example that people show all the time. Now, the people, which face is in front?
The one that's up front.
The one
that's closest.
I think most people put this face as in the
Yeah.
front, even though there's no reason to think that. This face might equally be in front, and if you look at it upside down, that's a harder exercise. Then that face looks to be in front. You can try it. We'll see in a moment one theory for why the brain sort of resolves that conflict that way. One example from my own research where you have some kind of a conflict resolution, perhaps, is related to what you feel while walking on a moving walkway. So when you walk on a moving walkway, so people have done experiments measuring, or observations measuring speeds at which people walk in airports. In an airport, you measure just people walking on the side of the moving walkways. They walk at some speed. On the moving walkway, people walk at a slightly slower speed relative to the moving walkway. You might ask why. One reason, of course, is that well, the walkway gives them some speed, so maybe they're taking advantage of it. They don't want to waste energy. That's one reason. Another potentially plausible reason is that there is a sensory conflict, right? So when you're walking on level ground every day, there are multiple ways in which you get information about the speed at which you walk. One is called visual flow. The world moving past your eye tells you how fast you're going. And then, of course, there are sensors, lots of sensors in all your muscles that tell you how hard your muscles are working, that tell you how fast you're going. And these two sensors agree with each other when you're, or at least you've trained those sensors when you're walking over ground. But when you're on the moving walkway, there's a conflict, right? So for a given speed, you feel the speed that your eyes see is much faster than the speed the legs feel. You're sort of zooming past when the legs are not working so hard. So there's a conflict, and very often the brain sort of resolves that conflict somehow. Maybe some of you feel weird while walking on a moving walkway, the speed conflict thing. And typically, well, we like to think that the brain does some optimal conflict resolution, but in the simplest sense, it does an average or something. And if you assume that it does an average between speeds estimated with these two sensors, then you would predict that you would walk a little bit slower on the moving walkway if you wanted to really walk at the same speed as on solid ground. If that was your goal, and if you use these sensors to walk at the same speed, you would walk slightly slower. So that's an explanation for this sensory conflict resolution. Maybe last slide. Okay. And another sort of sensory conflict resolution is this notion of using your past experience to inform how you resolve or how you figure out what's happening in the real world. And people particularly use the word Evasion, which is you have some expectations, some probability distribution over all the things that can happen in the world, and then your sensors tell you this is what happened, but then you don't believe the sensors completely. You do some mixture of what you think should happen with what your sensors tell you, and you sort of arrive at some intermediate thing. So one common theory of why the Necker cube looks like this face is in front is because in most of our experiences, so the theory goes, you're looking at cubes from the top, and this would be consistent. This face being in front would be consistent with that sort of viewpoint. So this would be a Bayesian accounting of why that face looks like it's in front. So maybe I'll stop there.
Yes.
Cold time.
Yeah.
Got maybe 5 minutes to stay within the same framework. So we'll have questions for Manoj related to this field.
Well,
So far.
can the question be, can we see other slides?
Well, that's also possible. Just to warn you, we've got 5 more minutes in Manoj's time slot. So.
How many more slides do you have?
Oh, four slides?
A title like that.
Yeah.
Well, I don't know if this is,
Oh, is this the
Keep going.
trampoline one? Okay.
Yeah, get
Please continue.
Go ahead.
Show us the video of people fighting on trampolines and we'll move from there.
so that's a conflict. So conflicts, I guess, conflicts as usually sort of conceived in game theory so I guess the conflicts that I was talking about in the first half of the talk are with yourself, so to speak. You have a system, and the system has either conflicting goals or conflicting information, and the system tries to resolve it as best it sees. And the more sort of traditional form of conflict is conflict with another person, another entity which has its own interests, which are different from your own interests. And that's sort of the purview of game theory, I suppose. In this particular, it's sort of the only piece of work that we did in game theory, barely. This particular game is called Seat Drop War. Who's played this game? It's called Seat Drop War, apparently, at least in some part of the United States. And the goal is to
I played one where you bounce someone off the trampoline.
well, here the goal is to, so let me actually show this video. So you bounce on your feet and on your seat alternatively. And the goal is to be the last one still bouncing. It turns out that in these games, as people sort of continue to sort of bounce back and forth, occasionally there is something catastrophic happens in that one person loses all the energy very suddenly, and another person gains all the energy and gets sort of shot up into space or something. Right? So you will notice that this game ends with this girl barely bouncing and the other girl sort of bouncing way high. So she barely bounces, she bounces much higher. It's not that dramatic. but
She seems very excited though.
so the red girl barely bounces, the other girl bounces. And there's a whole championship, so we found on YouTube the Dublin something championship of seat drop bar or something, where we found 20 videos and I wrote to him and he sent me all the videos. That's pretty awesome. So I learned about this over dinner with one of my friends, and I thought maybe we can cook a little mathematical model of this game. But before that,
So I'm gonna give you 2 more minutes.
okay. So these are some experiments that I did. So it's not just people that have this catastrophic energy transfer. You can do it with balls. If you drop balls on a trampoline, one, and they drop them just right, one will bounce way higher than another. And it has to do, it turns out, with the smallest time. So energy can get transferred between the people or the balls only if they're both in contact with the trampoline simultaneously. Otherwise, there's no way of transferring energy. So the trampoline somehow transfers energy. So the strategy in the game is to time your jump or whatever, or extend your leg in a manner that makes you fall or land on the trampoline just the right time. Right. So it's a standard game. So you can make up a little model of two people, and all they have control over are their leg lengths, and they are supposed to choose their leg lengths so that they time their landing so that they get the energy from the other person or something like that. I've used some jargon here, which maybe we don't have time to talk about. But the game theoretic solution is that, well, if we start from both roughly the same symmetric height, you would do the same thing forever. Your legs need to be same. And it turns out that small deviations in initial energy, if you do the optimal thing, will grow over time. Slight asymmetry will grow over time, it turns out. So this is sort of a simulation of essentially passive bouncing of two balls. Sort of fun to watch. So this is people, I guess people holding their legs at zero height or something, zero length or something.
So are
What?
humans
What?
are humans engineered as it were in
Yeah.
such a way that we happen to walk efficiently, or do people learn to walk in the way that they use the least energy given their height?
I think there is a lot of learning. So I guess it's not related to this video, but there is a lot of learning for sure. But people have done experiments where we did experiments. You ask a person to walk, constrain a person to walk in a weird way. Maybe I'll stop the video so people are not staring at it. So we asked people to walk sideways at their natural speed. And these were not habitual sideways walkers. And we measured energy cost as a function of speed, sideways walking speed. And the first time they ever walked sideways, they picked a speed which is incredibly close to their energy minimum. So over the last 20 years, you've sort of figured out how your legs work and what the optima are, it feels like.
Don't tell me what
I have. So it feels like people are very good online optimizers in that they figure out what approximately is the right thing to do almost immediately for simple tasks. If you have very complicated tasks, it can take years, hundreds of years. The classic example, of course, is athletic events, right? So. Maximum performance at athletic events. For instance, high jump, forever people were, this is the bar, people were running up and jumping over sort of chest on. And then in the 1960s, some guy figured out that the better thing to do is to jump with your back to your to the bar. It's called the Fosbury flop. But that took hundreds of years to figure out. But that happens occasionally in extreme sort of applications.
So in the interest of time and to be fair to Susan, I'm going to stop this session here.
Yeah. That sounds like
Take a couple of minutes.
That's a lot of pressure on me, right?
Grab some people. It sounds like you let us off and have them hobble around.
25.
What's wrong with that? I heard that.
Like watching it forever. That'd be great.
Hold my presentation and watch basketball.
It's really relaxing.
Manoj, if this coherent doesn't work out, you could be like a screensaver.
Our
I
first,
know, I love it. It's just like I'm like enraptured by bouncing objects.
our first commercial product.
I'm not sure.
Factory savers.
Steam
Steam
savers.
savers.
What does LSU take? 50%.
Yeah, cut the camera.
But that's a programming language. But yeah.
I know you can do that now.
You can do anything in MATLAB. that's but I mean you have to write the equations that describe it, right? So I wrote them, and then it's a bunch of differential equations that you can solve.
I used to stare at a oscilloscope so
Well, I
long
don't know,
when I was
it's
a
like, you
kid.
know,
So this is
you can do many things in SAS, but they all look ugly.
In bright spinning
SAS. No, you can do more things in MATLAB than
No, but I am
Yeah.
thinking serious, you could convert that to
That's
pitches or
exactly.
tones or something.
Sonification.
Yeah.
Be an output file that says.
Well, all
I
kinds
guess-
of chemicals are becoming
Yeah.
legal, we have a market.
Is there a physicist in the audience?
No.
There are some engineers.
People that do molecular dynamics. No one?
Oh, I did a little bit of molecular
So
dynamics.
that thing is sort of like molecular dynamics. It's a purely deterministic system.
Yeah.
There's no randomness. But you start off and simulate, and it's energy conservative and so on. You start off, you simulate forward in time. You get incredibly complicated what is like stochastic. It becomes, of course.
I think it must have been.
Use the door.
Oh, it's dangerous. Is it twisted?
Well, I've got, she might have, she has one on in case anything comes. How many famous things already go down to the side? I don't think how to organize them. How the organizing goes with the organizing. I'm sorry, what? It's like how many scheme exchanges have you been to?
32 is the third, right?
Yeah. That's what I thought, but I was like. I was like, I was getting there in front of them. I remember Mike talking at one.
Yes. You don't want to do that. I mean, I don't need it. I just want it.
That's for the people that don't come regularly. See if people actually come back. We need to put that in anyway.
Easier than flies.
I'm making Susan
And Manoj.
Please keep me going. I want to outfit a jetpack onto
Yeah.
Right.